1.9 will be a little bit of a breath of fresh air because 1.9 is like 2.5 pages long, and there's only one theorem in it, so it's just a little bit of terminology. 1.9 deals with the transpose of a matrix. And to transpose a matrix, we basically take the first row and rotate it into the first column. Second row, rotate it into the second column. Third row, rotate it into the third column. So if matrix A is, let's say, 1, 2, 3, 4, the notation that we use to represent the transpose is a superscript T. So the transpose of A, we take the first row and we write that as the first column. So 1, 2 becomes 1, 2. The second row becomes the second column. So 3, 4 becomes 3, 4. So this is the transpose of A. Now, a matrix doesn't have to be a square matrix. Every matrix has a transpose. It doesn't have to be a square matrix or invertible or all of that. So let's suppose we have this matrix, which, keep in mind, is a 3 by 2 matrix. 3 rows, 2 columns. And then the transpose of that will be a 2 row by 3 column. We'll take the first row, and that will become our first column. Row 1 is 1, 2, so our first column is 1, 2. Second row becomes the second column. Third row becomes the third column. And yes, that is 2 rows by 3 columns. Notice you can always multiply a matrix by its transpose. If, say, matrix C is M by N, then C transpose would be N by M, because this number of rows, we swap rows with columns, so this number of rows becomes this number of columns. So if we were to try to multiply those together, we would have an M by N times an N by M. Those have to match to multiply 2 matrices together, and our output would be an M by M matrix. So you can always multiply a matrix times its transpose. Any matrix has a transpose. Another definition is what's called a symmetric matrix. In order for a matrix to be considered symmetric, a matrix and its transpose have to be equivalent, equal to each other. An example of that, I believe, would be this. Notice if we transpose that, our first row would become our first column. Our second row would become our second column, so this row becomes this column, this row becomes this column, and notice those things are identical. So this is what's considered symmetric matrix. Now they just list a few properties for Theorem 1 in this section. They say let A be an N by M B be M by P. So notice you could do A times B if necessary because they have the n, these numbers are the same. So one characteristic is that if we have A transposed and we transpose that, then we end up back to the matrix we started with. Think about it. If you take A and swap its rows and columns, and then swap the rows and columns again, then you're just swapping back to what you started with. If we have a product of two matrices and that product is transposed, that's equivalent to the second matrix transposed times the first matrix transposed. Notice the swap in order. When we apply our quote-unquote exponent, the order of these matrices swap. And we've seen that back in the last section when we dealt with inverse matrices as well. They say if A and B are n by n by m, so they're the same size, then if we were to add A plus B and then transpose it, that would be the same thing we would get if we transpose A, transpose B, and then add them. And then lastly, if A is invertible, then the transpose of A is also invertible. This is pretty much all the new information for 1.9, transposing matrices. So I'll give you a number of problems from 1.9, and then we'll discuss those in the future.